Okay, so welcome to our session with mechanics with dynamics, and the first talk is from the physical stability of a place with a place with a mixture of metal. This one.
Dear colleagues, let me talk about stability of shock waves in a two-phase vapor-liquid mixture of a metal. So this work deals with thermodynamic properties of materials. We need to know equation of state and some dynamic properties to make numerical simulations of different processes. Here you can see some illustration of example of such a process where one metallic plate, titanium, for example, impacts on aluminum plate with high enough velocity, about 10 kilometers per second, and shock when first plate impinges to second plate, shock waves propagate on impactor and the target. In this shock wave, state of material from initial point, initial state goes to state on shock Gaussian curve of both materials. This points B on phase diagram. This phase diagram for titanium, temperature versus density, and for aluminum also temperature versus density. When shock wave reaches back surface of plate, release wave will go backward, and temperature and density and pressure and density will decrease. Material will expand and some state of evaporated material will be realized. First, this expanded, extended state of material at negative pressures will be realized, and then this metastable state will transform to liquid vapor mixture. Also, another example of such process where we need to know equation of state of material over a wide range of temperatures and densities. This process is interaction of ultra-short 100 femtoseconds laser pulse with metal, gold, for example. So this is ultra-short laser pulse, and it just hit the material at a constant density, isochorically heating. These trajectories show change of material's state with time on different depths from target surface. outer layer is evaporated almost completely, and here you can see isochoric heating and shock wave propagation inside the metal targets. Here you can see a diagram of states of aluminum. This material is widely investigated in experiments at high pressures and over a wide range of densities. Here you can see lines. This is calculated shock adiabats. Markers denote experimental data from shockwave experiments. These crosses show results of experiments with electrical explosion of metallic foils. So also you can see these dotted lines. These are expansion isotopes of metal from shock compressed state up to low pressures, and here with this expansion state of two-phase liquid vapor mixture can be realized. To describe thermodynamic properties over a wide range of pressures, volumes, and temperatures, we need to know equation of state, and this equation of state determines two-dimensional surface in three-dimensional space, like here on this slide. All processes in this material will take place on this two-dimensional surface. Not higher, not in this point, but only on this surface. So if we will know equation of state, we can predict most behavior of materials in different processes at high densities, at high pressures, at high temperatures. Red lines here show phase boundaries, melting curve, evaporation with critical point. Blue lines are shock adiabats of solid and porous samples of metal, zinc, for example. Green lines are release isotopes. So, equation of state model is based on semi-empirical for wide range parameters. Is based on semi-empirical approach, which was proposed and developed by many scientists, Lev Altshuler, Samuel Kormer, Vadim Orlin, Alexey Bushman, Vladimir Fortov, Gerard Kerli, David Young, Keslin Polian, Igor Lomonosov, and others. Present model is modified after Bushman model, with taken into account harmonic approximation or wide range of temperatures, and Thomas Fermi model at very high compression ratios, up to 1 million fold compression. And also phase transitions are taken into account, like melting, evaporation, and polymorphic transformations in solid phase. This equation of state can describe metastable states of material. So formulas are simple enough, but there are many formulations. I will explain only main features of this equation of state. It's based on Helmholtz free energy potential as function of volume and temperature. In general form, it consists of three parts. First is cold for cold material at 0 temperature. It depends only upon volume. And second and third parts describe thermal contribution of atoms and electrons. All three parts are formulated for different phase states of material. Here you can see first component, the cold curve for solid phase. Here sigma c is compression ratio. This for compression region, and this formula is for expansion region. E sub is energy of sublimation. And also second term for solid phase. It takes into account acoustical and optical modes of vibrations of crystalline lattice. Here D is Debye function, and also anharmonic contributions can be taken into account. For liquid phase, both first and second terms takes into account changing of density at melting point and changing of enthalpy at melting point at, for example, atmospheric pressure. Last part, electronic contribution, is described by in the same manner like in Bushman model. Here you can see formulas. And some results of calculation for different materials. This is tungsten at 0 temperature, cold curve, pressure in GPA. This is very high pressures, and compression ratio. This means density divided by normal density of material. Black line is from these calculations. Squares are taken from calculations by Nikolai Nikolaevich Kalitkin using Thomas Fermi model. This model describe material at very high pressures, at very high energies. And you can see that this our model agrees well with results of Kalitkin. Here you can see example how calculated shock adiabats corresponds to experimental data from shockwave experiments for two materials, titanium and tin. So you can see good agreement of result of calculated curves with experimental data. And here three formulas are presented, which are used to calculate shock adiabat. These formulas represent conservation laws for mass, momentum, and energy. Mass, momentum, and energy. Also, here you can see phase diagram of tin, temperature versus pressure. Lines are calculated using this equation of state. Markers correspond to temperature measurements at high pressures. All of these points correspond to melting curve and obtained using different methods. To calculate boundaries of phase transitions, we need to solve for system of two equations for Gibbs energy of two phases under equilibrium and pressures. Result will be volumes or densities of two phases at which are in equilibrium at a given temperature. Here you can see calculated shock adiabats. These two lines for solid and porous samples of tin. these lines correspond to release isotopes. Here, these isotopes are compared with experimental points. This change of slope of this release isotopes correspond to beginning of evaporation of material at expansion. Here material is one phase state, and here in two phase states, liquid and vapor. Also phase diagrams of aluminum pressure versus specific volume at negative pressures, and density versus temperature. Same phase diagram, but here you can see that at negative pressures there are regions which can be reached in experiments with expansion of material with fast expansion of material in experiments with shock and release waves. And some results of calculations of shock adiabats of liquid and vapor mixtures. So inside the region of evaporation, this solid line is boundary of liquid vapor domain for material, tungsten, for example, pressure, specific volume. Lines correspond to shock adiabats, where initial state of material is inside this binodal line.
And where is liquid, where is vapor?
Liquid is at small volumes.
And at liquid?
Yeah, here gas phase.
Oh, so it's not liquid, it's gas.
Yeah, liquid, gas.
Gas.
Gas correspond to higher volumes. And here inside there is a mixture of
two phases.
Yes, two phases, mixture of two phases, and all of these shock adiabats are calculated in approximation that in each point this mixture of liquid and gas is equilibrium. This is the reason that this shape of shock adiabats is so surprising. For example, here, first with increasing pressure, mixture is compressed, then final volume is decreased. Here, this adiabat goes to one phase region. At higher densities, and lower volumes of two-phase mixture, we obtain another behavior when first this two-phase mixture is compressed, then shock adiabat goes along a region of liquid phase, one-phase liquid here. Then adiabat goes again inside the two-phase region, and so exits from two-phase region on gas side. Okay, we can see here that this dash boundary, which shows unstable state of this shock compressed mixture. Stability criteria of shock wave instabilities are first proposed by Dyakov, 1954, and developed by Kantorovich, Paulis, Kuznetsov, and other authors. Here you can see conditions of corrugation instability and also sound instability. Sound instability means that shock wave is stable, but it is a source of sound waves, which can decrease energy of shock compressed material.
We have time limits, 20 minutes, including questions.
Okay. This is last slide. It shows boundaries of sound instability region of shock compressed liquid vapor mixture of tungsten. So yeah, but this this region, yeah, so if two-phase mixture has initial state inside this boundary, shock wave will be neutrally stable, but sound instability will take place here. These are my conclusions. Proposed approach is very good, and some stability, some regions of shock wave stability are calculated, and the obtained equation of state can be used in numerical simulations of different processes in materials under high pressures, high temperatures, high energy densities. Thank you for your attention.
Thank you. A couple of questions. We don't have time. Actually, I have one fundamental question. Where these processes are happening? I just cannot imagine this. Okay, yes, we have high temperature and high pressure, but where exactly this can be?
Where?
Where? Yes. Because we started with this process without introduction, where it happens, where it takes place. And I just cannot imagine in which technology uses this.
Which technology, how to make diagnostics of such things?
No, where this
How
process
realize?
Yes,
Yes.
just the shockwave technology, where is it realized?
Yeah.
Shock tubes, or just in hypervelocity impact?
Yes.
What were the methods for?
Yes. So this beginning of my talk was like introduction. For example, such process may be obtained at hypervelocity impact of some bodies. For example, maybe you know that about something about space garbage.
Space debris. Space
Yes.
debris.
Yes.
Okay.
This
Debris.
this
Space debris.
this debris are small parts of space vehicles in cosmos.
In the outer space, in low Earth orbits.
So,
Then
so
they can
small
collide.
part of this space debris
Yeah.
may make damage of some
Yes, but the question was
Sputnik.
not where is it applicable, but how just in
how
the,
obtain.
yes, in
how
the
up-
ground-based
yeah.
experiments you simulated
No, my question
this
is
kind.
even simpler. So, for example, I know scramjet, so there is supersonic flows, but it's air, so it's gas. I know interstellar, for example, gas, there we also have shock waves. But where this process happens, because metal and shock waves, they're completely different things for me.
Well, then probably it's necessary to look up in the continuum mechanics textbook better. That's where this process is. Shock waves and metals. Part.
В природе много где получается такие процессы. Вот. Не всегда они желательны. В технике, в частности, вот, для исследований, они получаются специально для того, чтобы исследовать в лаборатории, чтобы получить такие же состояния, просто чтобы знать, построить модель и предсказывать. Конечно, разрушение космического аппарата никто не сможет поставить там эксперимент, пронаблюдать. А промоделировать можно, и, в принципе, эксперименты покажут просто, насколько модель близка или далека. Позволит какую-то защиту космического аппарата разработать. Вот, то есть ударные волны — это способ для исследования свойств материала в первую очередь. Я так думаю. А вообще очень много экспериментов проводится, потому что много где это требуется. Не только в военных целях, но и вполне себе в мирных.
I think we can continue on our welcome party.
Да, но по поводу ударных волн все-таки, по поводу ударных волн в металлах, ну, чтобы уж это не оставалось так вот неизвестно аудитории, это очень часто используется во многих местах, например, сварка взрыв. Вот у вас летит со скоростью несколько километров в секунду лист на другой лист и сваривается. Вот там распространяется волны. Средняя скорость в стали волны от 5 километров в секунду и выше. В зависимости от вот. Где достигаются эти условия? Вот, пожалуйста, второй случай, это удар любого снаряда об броню.
То есть там тоже сверхзвуковые уже возникают?
Да, сверхзвуковые там возникают процессы, а когда отражается от внутренней поверхности брони, там возникает волна разгрузки, разряжения. И после этого возникает откол, явление тыльного откола, лицевой откол и тыльный. Все это волновые процессы. И вот везде вот ударные, вот такие ударные волны. Я уж не говорю о высокоскоростных соударениях, а вот обычно. Самый простой это сварка взрывов. Если у вас угол наклона плит такой, что он опережает скорость волны, то у вас просто не сварится.
От 8 до 12 градусов.
Okay, thank you very much. And next talk is from Puskov. On the LS stage, maybe I'm wrong, immersive boundary cancel messages of Airfoil addressable for simulation around Airfoil system. It will be online, so online.
Good afternoon. My name is Valeria Puzikova. I apologize for not being able to connect a video. My co-author was ill and I learned that I will make a report a few hours ago. Theme of my report is on the LSTEC immersive boundary Quetzal method usage for numerical incompressible flow simulation around Airfoil system. Here you can see an outline of my report. Flow-induced vibrations occur in tubes of heat exchangers and reactor rod systems under the influence of unsteady hydrodynamic forces. These vibrations can cause the destruction of the whole device due to incorrect choice of working flow velocities. Therefore, simulation of tube bundle flow-induced vibrations is a very important problem. To simulate these flow-induced vibrations, it is necessary to solve coupled hydroelastic problem. Such problems are complicated for numerical solution, since it is necessary to take into account interference between the flow and moving immersed body. So an immersed body and the fluid should be considered as coupled system. In case of sufficiently massive body, this problem can be solved using step-by-step numerical algorithm. Firstly, simulating flow around a body, moving with known parameters, and then computing dynamics of the body with known hydrodynamic loads. On this slide, you can see governing equations. The problem considered in unsteady case when the flow around an airfoil is assumed to be viscous and incompressible. The airfoils are rigid and can oscillate with 1 or 2 degrees of freedom. In case of hydroelastic problem statement, it is necessary to solve Airfoil dynamics equation together with flow equations. It is need to choose numerical method to solve the problem. The advantage of immersed boundary methods over a method with a body-fitted mesh is their computational efficiency. They don't require grading when domain shape changes in the simulation process due to hydroelastic body motion. In these methods, the irregular boundary is not is not aligned with the computational grid. Cells which the immersed boundary intercepts are the so-called cut cells. These cells contain the solid part together with the liquid part. The treatment of the cut cells is the most important issue of immersed boundary methods. And the LSTEC cut cell immersed boundary method for viscous incompressible flows simulation combines the advantages of immersed boundary methods and the level set method. This method allows to solve problems on the Cartesian grid. In contrast to classical immersed boundary methods, the flow variables are computed in the cut cells and not interpolated. Numerical analogs of conservation laws satisfaction in all fluid domain cells is a basis of LSTEC discretization constructing, which allows to obtain physically realistic numerical solution. For these reasons, the LSTEC method is used in the present study for simulation of tube bundle flow-induced vibrations. In the LSTEC method, staggered Cartesian meshes are introduced in the rectangular computational domain. Unknown components of velocity vector are computed in the middle of fluid parts of the cell faces. Pressure and normal stresses are sampled in the center of cells, and shear stresses and level set function are sampled in the corners of cells. The level set function is introduced for immersed boundary description. The immersed boundary is represented by a line segment on the cut cell. The cell face fraction ratios are introduced for efficient computation of geometry parameters of cut cells and identification of cut cell type. They represent the fluid parts of the east and north faces of cell. In a two-dimensional case, the cut cells can be classified into trapezoidal, triangular, and pentagonal cells. Position of the point at which the shear stresses are sampled on the cut cells depends on cut cell type. The arbitrary Lagrangian Eulerian method is widely used by finite volume methods on body conformal meshes. This method considers a computational domain that tracks the moving boundary such that the grid follows the boundary motion in the Lagrangian fashion, while it is held fixed in a Eulerian manner sufficiently far from it. And the ILE equations of the flow motion written in the computational domain are similar to the Navier-Stokes equation, except the convective term. In a series of papers, Farhat and co-workers have shown that LE numerical scheme preserves the accuracy and stability of its fixed grid counterpart if the grid velocity and mesh update procedure are designed such that the so-called geometric conservation law is enforced at the discrete level. This equation is obtained by requiring that a uniform flow is the solution to the ILE equations and states that the change in volume of a cell during a time interval must be equal to the volume that has been swept by the cell boundary. For immersed boundary methods, geometry conservation law is easier to fulfill because only the grid nodes on the solid part of a cut cell are moving, and the computational grid is not deformed by the immersed boundary motion. Convective terms are represented as the sum of fluxes through the elementary phases of control volumes. Central interpolation is used. Discretization of the convective fluxes on the immersed boundaries is adapted to each type of half-cut cell. The time integration of the differential algebraic system is performed with a semi-implicit Euler scheme. Predictor step leads to discrete analogs of the Helmholtz equation for velocities prediction, and the character step leads to discrete analog of the Poisson equation for pressure correction. Linear systems are solved using the FGMRS method with the ILU and multi-grid preconditioning. A number of model problems had been considered before simulation of tube bundle, flow-induced vibrations, flow around fixed system of circular airfoil wind resonance, and buffeting, which are presented now. To simulate wind resonance phenomenon, we considered the motion of the circular airfoil across the stream with 1 degree of freedom. Airfoil's constraint assumed to be linear viscoelastic, and airfoil's motion is described by the following equation. The natural frequency of the system can be set by varying of the coefficients elasticity. Number computations were performed on non-uniform grid with the following parameters. Computational results are in good agreement with the previous studies. Maximum amplitude is about 40% of airfoil diameter and occurs when the natural frequency of a system is close to Struhal number calculated for a fixed airfoil. Qualitative differences in airfoil's dynamics at Struhal numbers in the investigated region are shown here. Slight airfoil vibration is observed when the natural frequency of the system is significantly less than the frequency of vortex shadings. Damped beats appear with increasing natural frequency as you get closer to the Struhal number. Amplitude of the oscillations increases sharply near the frequency of vortex shading. Beats disappear and amplitude continues to increase with time. Amplitude of the oscillations decreases sharply and beats are observed again with a further increase of the natural frequency. Also, we considered the motion of the systems of circular airfoils across the stream with 2 degrees of freedom. Airfoil's constraints assumed to be linear viscoelastic, and airfoil's motion is described by the following equations. To simulate a buffeting phenomenon, we considered the motion of 2 equal circular airfoils at the following parameters. Since the distance between the airfoil centers along horizontal axis is large enough, upstream airfoil behaves like a single airfoil, and downstream airfoil performs forced oscillations due to periodic vortex shading flow past upstream airfoil. Thus, the buffeting of downstream airfoil is observed. The obtained results are in good agreement with the known data. Flow pattern depends on the tube's arrangement and the tube locations in the bundle. For this reason, we considered flow around 6 columns of tubes in staggered arrangement and flow around 5 columns of tube in inline arrangements. In case of staggered arrangement, two different frequencies are observed. For tubes from even and odd columns as an experiment. Upper frequency is observed in the tubes from odd columns, and this frequency is considered as the vortex shading frequency. Lower frequency is observed in the tubes, and it corresponds to frequency of vortex straight interaction. Computational results are in qualitative agreement with the experimental data. Tubes from first column behave like a single airfoils, and in case of staggered tubes arrangement, amplitude of the tubes oscillations along vertical axis significantly decreases with the increasing column number. In case of inline tubes arrangement, amplitude of the tube's oscillations along vertical axis significantly does not decrease with the increasing column number. Tubes from first column behave like single airfoils, and these computational results are in qualitative agreement with the experimental data. So a software package is developed for the numerical simulation of the airfoil's motion in the viscous incompressible flow by using the XLIX method. Simulation of a circular airfoil, wind resonance, and buffeting phenomena, tube bundle flow-induced vibrations are considered. The XLIX method allows to simulate these phenomena on a very coarse mesh. Computational results are in good qualitative agreement with the experimental data. As future directions of our research, we want to know the usage of other approaches for turbulent flow simulation in XLIX method and flow simulations at high Reynolds number. Thanks for your attention.
Questions, please?
Okay, can I ask a question, but I don't know if the presenter can hear my question. Can you hear me?
She has to hear it.
Oh,
The mic is working. She has to hear it.
yes, but maybe you can answer. Just one. Okay, just please, can you show the governing equation for the airfoil motion? Where, for example, for just a simple case when just have only one airfoil for, well, okay, this is for the two, it doesn't matter actually. This F, A and F, D, how do you determine these terms? So this is the external force from the flow. How is it determined? I can't hear anything. Maybe it's necessary coming more close to the screen, or I don't know.
Excuse me, I don't hear you.
You don't hear me, and now do you hear me?
Yes, I hear you very bad.
Very bad. Okay, the question is, how do you determine these F, D, and FA terms? Yes. In these equations, how these terms are determined? Значит, да, как определяется сила F и что такое коэффициент B? Потому что сила F и коэффициент
B,
да.
это затухание. И про силу вы спрашивали, да, насколько это?
Затухание – это сопротивление некое, зависящее от скорости. Сопротивление средой обозначено. А сила F – это тоже воздействие среды. Вот поэтому у меня и вопрос. Не считаете ли вы здесь одно и то же дважды? Не учитываете. Потому что затухание – это сопротивление среды. А FD и FL у вас – это тоже влияние внешней среды. Вот как вы разделяете влияние от сопротивления? Или у вас внешняя задача идеальной жидкости обтекания решается?
Так, сила F, здесь у нас имеется в виду гидродинамические силы. Да, в первом уравнении это сила лобового сопротивления, во втором уравнении подъемная сила.
Когда решается задача, вязкость есть там или у вас идеальная жидкость?
Что нет, жидкость не идеальная.
Не идеальная, значит вязкость есть. Что такое B? B, зависящее от скорости движения, это тоже сопротивление трения. Только трение зависит линейно от скорости. Вот поэтому вопрос, зачем два раза учитывать одно и то же?
Разрешите, я попробую ответить, как
Что одно и то же?
Ну хорошо, давайте.
Да, ну так, вроде, значит, коллеги, значит, речь идет здесь вот о чем. Действительно, силы, компоненты силы, которые здесь указаны в правой части, это составляющие гидродинамической силы, которая, разумеется, включает в себя силу, так сказать, связанную с вязкостью, да, безусловно. Тогда как коэффициент B, значит, который можно рассматривать как коэффициент демпфирования, так, иногда двоечку там указывает еще перед ним, это трение, которое, скажем так, диссипация в механической системе. Это не, так сказать, вязкое трение, связанное с жидкостью. Это трение в самой механической системе, не трение, скажем, диссипация энергии.
Пружине. Вот у вас
пружина, связь, да,
вот
совершенно
последний член – это упругая энергия, вот у вас она
это
пружина.
Понятно, да.
И вот эта пружина еще в какой-то трубе,
значит, тут, да, такая модель, ну, конечно, упрощенная.
Все, я все понял.
Потому что реально это, скажем, пучок труб. И там, пружины как таковой нет. Эта пружина, она моделирует, скажем, первую собственную частоту колебаний, да, значит, так она настроена.
Это уже не понимаю. Вот трение в пружине, это понимаю.
Трение в пружине.
А вот первые собственные частота...
Но понимаете, в чем дело?
Значит, от скорости,
здесь речь идет... это модальное демпфирование. Модель модального... Извините за тавтологию, значит, как модальное демпфирование, которое будет иногда в механике. То есть здесь это, скажем так, простейшая плоская модель какой-то реальной системы, трубчатой системы трубок, которые находятся в поперечном потоке. Разумеется, они совершают определенные колебательные движения. Здесь рассматривается сечение, одно сечение. И для того, чтобы определенным образом смоделировать, пусть упрощенно, механику этой трубы, мы вводим вот такой фойхтовский элемент, да, значит, Кевина-Фойхта некий элемент.
Нет, это понятно, что это фойхтовский элемент.
Да.
Это мне было понятно еще, когда я на третьем курсе учился в университете. А спросил я именно... Вопрос был, что он физически моделирует. Но я понял ваш ответ.
Это
мне понравился ответ. Я думаю, что еще более правильно то, что я не понял. Но я надеюсь, что все там правильно. Спасибо.
Так, мы постарались как-то вдвоем этот вопрос.
Хорошо, спасибо. Спасибо докладчику. Вы храбро бились.
The next talk is from Ismailova Yulia.
Good afternoon. My name is Yulia, and I'm the student from the Bauman Moscow State Technical University. And today I would like to present to you my topic, my report on the topic the T-schemes for the boundary integral equation, solving in vortex methods of two-dimensional flow simulation around airfoils. The viscous incompressible flow is described by a system of Navier-Stokes equations. The first one is the mass acceleration law, and the second one is momentum balance equation. This system has to satisfy the perturbation, decay at infinity, and the no-slip boundary condition on the walls. To solve this problem, there is a whole family of the different numerical methods, which is divided into two large groups. The first one is variant mesh methods, which includes finite volume method, finite element method, finite difference methods, and others. And the second one is Lagrangian numerical methods. These include vortex methods, smooth particle hydrodynamics, and others. In this work, we will talk about vortex method in more detail. The application area of dimensional vortex method includes the construction simulation with the subsonic flow and the quite a three-dimensional problems can be solved using plane sections method, and their compressibility in these problems can be neglected. Their vortex methods based on the Professor Nikolai Gorodjukov's idea about replacing the streamlined airfoil with a vortex sheet that had the same effect on the flow as the original airfoil. While simulating the flow around airfoil, the primary computational variable is the vorticity. By its distribution, it is possible to reconstruct the velocity field according to the Biot-Savart law, and the pressure can be reconstructed only according to the analog Cauchy-Lagrange integral. Usually, in the framework of the vortex methods, the number of problems is solved. The first one is the vorticity evolution in the flow domain. The second one is the estimation of hydro or aerodynamic force acting on the structure, and the third one is the no-slip boundary condition satisfaction, which is provided by vorticity generation on the walls, and the vorticity is modeled by vortex sheet intensity being generated at the airfoil boundary. The aim of this work is to develop and to implement numerical schemes for the boundary integral equation solving in vortex methods of two-dimensional flow simulation around airfoils.
Just a second. And if you could, can you stand a little bit closer to the microphone? Yeah.
There are two approaches to satisfy no-slip conditions on the airfoil boundary. The first way is widely known and is called N scheme. It can be obtained by projecting the integral equation onto the normal unit vector, and this approach provides the non-true condition satisfaction. And this approach leads to singular equation of the first kind with a non-integrable kernel of the Hilbert type. By projecting the integral equation onto the tangent unit vector, we satisfy the no-slip condition. This approach is called T-scheme and leads to Fredholm type equation of the second kind with bounded or at least absolutely integrable kernel. Galerkin method for the boundary integral equation solving. The airfoil should be replaced with a polygon. The polygon edges we will call the panels. Mathematically, the no-slip boundary condition is equal to the boundary integral equation. To solve it, we we present the solution as by the decomposition of basis functions according to the Galerkin method. The coefficients should be founded from the orthogonality condition for the residual of the integral equation to the projection function coinciding with the basis functions. In this work, the piecewise constant and piecewise linear schemes will be considered. Using piecewise constant scheme, we assume that their solution on the each panel is a constant value, so we choose basis functions as constant functions. In the case of piecewise linear scheme, we represent the solution by combination of piecewise constant basis functions and piecewise linear basis functions. So the solution on the each panel is a linear function. The solution of the resulting boundary integral equation is not unique. So the unique solution condition is added and is equal to the value of total circulation. By the developed numerical scheme structure, the piecewise constant scheme error provides the first order of accuracy, and the piecewise linear scheme provides the second order of accuracy. Here on this slide, it is shown that the piecewise constant scheme really has the first order of accuracy, and the piecewise linear scheme has the second order of accuracy. Piecewise constant scheme metric size is n+1 squared, and piecewise linear scheme metric size is 2n+1 squared. It is possible to construct the scheme with piecewise linear scheme accuracy and piecewise constant scheme computational complexity. We assume that the solution is continuous on the Airfoil boundary, and we introduce the basis function using in finite element method as basis functions. If the solution is bounded but have finite jump, the previous scheme can be modified by adding a new basis function at the node where discontinuity of the solution should be taken into account. Here it is shown the application of development of our numerical schemes in comparison to exact solution for the Zhukovsky wing airfoil in relation to vortex sheet intensity. Note that the solution is bounded. Next slide, it is shown that the solution is unbounded. All the statements about orders of accuracy are appropriate only when the solution is bounded. Here in the figure, the solution is unbounded, and the accuracy of numerical schemes drops sharply, and it leads to decrease.
And what is gamma small here?
Vortex sheet intensity.
So it's vorticity.
Yes.
Okay.
Well, the solution is unbounded, and the accuracy drops sharply. So it's necessary to correct our new numerical our numerical schemes, it is known that the asymptotics of unbounded solution had this form, where rho is the distance to the sharp edge, and the he is the outer angle. So we will consider the piecewise linear scheme for further correction. We will introduce the new basis function onto the first and the last panels, and so instead of piecewise linear basis function, we will use these new basis functions, but we leave the projection function we using in piecewise linear scheme. And this method corresponds to the Galerkin approach. Due to the fact that convergence analysis is non-trivial for unbounded solutions, we will consider a model problem with a known solution, and with using our unbounded solution. So we will consider the problem of calculating all the components of the added masses tensor. And this problem is equal to the problem of obtaining the 6 flow potentials, where phi is potential corresponding to the airfoil movement with a unit velocity in the chosen direction, or to the rotation motion with a unit angular velocity directed along the chosen axis. In addition to the vortex shift intensity, it is suitable to introduce the attached vortex shift intensity according to the rule. Galina Yakovlevna established the fact that all components of added masses tensor can be calculated according to their rules. As I said, we will consider a problem. With a known solution, which using our unbounded solution. So if we map a circle with this radius, which center is placed at this point on the complex plane zeta according to the rule, we will obtain Zhukovsky ring airfoil shown in the figure. And
what is the flow direction in this case?
What?
Flow direction. Where the flow goes? From left to right or from right to left? А то как бы слева или справа сейчас? Вот для этого.
We consider that the airfoil is moving
in which direction? Right
along the y-axis.
Okay, no flow. Потока нет внешнего. Просто движется вверх.
The airfoil just is moving up. And for this case, the solution is unbounded. So here are the tables showing the relative errors of the added masses tensor estimation for the weak airfoil for different numerical schemes, and the order of accuracy for different numerical schemes. From the tables, it can be seen that the accuracy of constant scheme and linear scheme, which disregarding the singularity of the solution, is lost. But the asymptotic scheme has their second order of accuracy as we wanted. So the results. The first one is the hierarchy of numerical schemes for the two-dimensional vortex method is developed based on Galerkin approach. Some of numerical schemes provide the first and the second orders of accuracy respectively for both smooth airfoils and airfoils with a sharp edge in the case of a bounded solution for the vortex shifted density. In the case of an unbounded solution, a new scheme was developed taking into account the solutions in reality. Thank you for your attention.
Thank you. Next talk is Franceschi. Yes.
Next talk. Okay, just when we have to wait some seconds, I want to tell you that, as you understand, in Bauman University we work on vortex methods of computational hydrodynamics that belong to a class of Lagrangian mesh-free methods. In the previous talk, Yulia described our results in the development of new numerical schemes of solving boundary integral equation arising in these methods. And in my talk, I want to just to describe briefly our results connected with three-dimensional flow simulation.
And maybe you will comment on the previous talk, just about this problem that the airfoil just moves up without any flow. So, which means the flow goes from top down. So, does it correspond to any practical case or case of practical interest? Because we fail to understand.
I will comment in briefly.
Yes.
Idea of that numerical example is connected with the fact that we want to obtain some known solution in order to have the possibility just to compare them numerically, and to estimate the order of accuracy of the developed scheme. As our colleague from Moscow University, from Mechanical Institute, Professor Klinikova, found a very close connection between added masses of the airfoil, well-known theorem of added masses, and the solution of the mentioned boundary integral equation. In order to estimate the values of added masses, or the components of the tether of added masses, it is enough to consider simply, in two-dimensional case, just three problems. In the first problem, we consider the airfoil moving horizontally in steel media. In the second problem, we consider it moving vertically in steel media. And in the third problem, this is rotational motion, again in steel media. It is having these solutions of these three problems, it is possible just to compute all the components of the tensor of added masses.
But as far as I remember, for the added mass tensor, it is necessary to have the accelerated flow, and not steady state.
But if we just consider the analogy, mathematical analogy, it is possible to consider just acceleration on the flow, I mean in numerical computation, during one time step. So we can just consider the problem when first we have steel media without any vortices, without any more, just steel.
Then you
begin we just perform one time step and solve our boundary integral equation. This is, and it depends the vorticity generated on the boundary, so we exactly simulate the accelerated
so, but velocity is still variable, because the next time step you increase again velocity.
No.
Or you keep velocity
it is enough to solve the problem only at one time step. Yeah. But yes, your remark is absolutely it's very correct.
Well, since you use the solutions of Deinikov, I know these solutions. That's why hopefully everything is correct.
Yes, this is very interesting work with the connection of this vortex approach and added mass theory. Very interesting. Okay, I will come back to my talk. Problem of three-dimensional flow simulation are much more complicated, of course, in comparison with two-dimensional approaches. So I just only want to tell that in two-dimensional case, a lot of problems can be considered maybe not to be solved, but investigated very, very carefully. In three-dimensional case, these problems are much more complicated from both theoretical and computational point of view, and I can only tell that vortex method are developed more or less only for some very narrow class of the problems when we deal with, for example, thin surface, some thin wings maybe, thin plates, some buildings and constructions, where we can just point out the line where we simulate the separation, where we simulate the separation of the flow from the surface. But if we want to work with more complicated flows, for example, if we want to simulate the vortex wake, for example, after the some plate, maybe thin plate, this is some model problem, at a large angle of incidence, we need to simulate not thin surface of vorticity, or not thin surface of the discontinuity of tangent component of velocity, which can be considered as thin vortex sheet in the flow, but we should simulate some distributions of the vorticity in a three-dimensional domain. Yeah? There are some approaches, most of them are connected with consideration of some point particles, which are considered as vorticity carriers. But in this approach suffer from a very strong problem, because if we consider just point carriers of vorticity, the vorticity field becomes not divergence free. This is not correct from the very basic, from physical point of view. So we suggest to consider the so-called vortex, closed vortex loop elements, when we consider vorticity to be represented as some, I can say, super element of closed vortex loop, maybe of very complicated shape, but it is closed. And if it is closed, so we automatically satisfy the divergence free condition. All problems can be solved, but the problem is that we should solve boundary integral equations sometimes on the meshes of a very, I should say, poor quality. We have cells with high aspect ratio, with very small angles, triangles with small angles, with high ratio of the areas of neighboring element, and so on. So we developed our method, which can work with triangular cells. This is most general approach. The mathematic idea is based on of our approach. I mean, is based on this unmentioned report here. And they, I mean, authors of this report suggested to use the so-called generalized Helmholtz decomposition, and they performed an idea of developing the so-called T-schemes, the approach of solving of the boundary integral equation with higher precision, I mean, in comparison with traditional approach. However, I have never seen some implementation of this approach, only some just brief words, brief description, and some results described qualitatively, I should say. Okay, I'll skip this slide. Idea is to we should perform the boundary condition of no-slip boundary condition. And again, as in two-dimensional problems, we can consider the first approach by projecting this equation onto normal direction. And from the second approach is connected with projection it onto tangent plane. In three-dimensional, it will be tangent plane. Yep. In the framework of traditional approach, we deal with hypersingular integral equation, and it is, I should say, not a trivial problem just to develop numerical scheme that allows us to obtain its solution with high accuracy, especially on non-uniform meshes. In the approach that we have developed, we again use Galerkin approach. We consider vorticity to be expressed as a linear combination of tangent vectors, and we consider it to be piecewise constant on each triangular path. In order to obtain the equations for this coefficients determination, we just project the residual of this equation onto two tangent vectors. So we obtain linear system. In fact, the main difficulty in this system construction is the computation of such integrals. So these integrals are, I should say, geometrical integrals, but it is a very non-trivial problem to compute it with high accuracy. In fact, the inner integral can be calculated analytically. This is just expression, and I should only notice that, for example, that the theta function has a very clear geometrical sense. This is just a solid angle. And psi function, this is some potential, some analog of potential. In order to compute the outer integrals, first idea is just to compute it numerically using some, for example, Gaussian quadrature rule, something like it. But if we consider panels, not neighboring panels, everything is okay. The accuracy is high enough and no problems at all. But if we consider panels with common edge or common vertex, if we just compute integral numerically, the error can have nearly the same order as the solution itself. So about 1% error can be obtained. We developed semi-analytical technique for such integrals computation. And idea is to just to split the integrand into two parts: singular one and regular one. Regular part is smooth function. It can be integrated numerically without any difficulties. And for singular part, exact analytical expressions for all the integrals are obtained. So the result is quite good, I should say. The error is just a small ratio of 1%. No. There are some examples of computations, and the last line shows the result. The last line shows the results of computation. I mean the relative error when we use the developed approach. The error is rather small. On this slide, you can see the result of implementing of our approach for simulating for some model problems. This is a sphere with non-uniform surface mesh. Traditional approach gives some, I should say, divergent lines, level set lines, but in exact solution, they should be exactly horizontal. Our scheme gives more or less a good result. And it's the advantages of our approach is much more clear if we consider the problem of the ring airfoil of finite span simulation. You see that the traditional scheme, which requires to solve hypersingular integral equation, leads to not very accurate solutions, not symmetric, while our scheme gives maybe not perfect, but much better solution. Here you can see some results about convergence of the approach. Both schemes provide the second order of accuracy, but our scheme that we call T scheme, the accuracy is approximately 10 times higher than the traditional approach. But here we consider sphere with uniform mesh. I mean. Okay, some examples of unsteady wave simulation, just maybe some joke example with some model sport wave. Yeah. Again, some results of verification of our model with on the problem with known exact solution is vortex ring and the sphere. It's interesting to note that if we trying to reconstruct velocity field very close to the body surface, in our T scheme, we can see the convergence of the result when we refine the surface mesh. I mean. But if we use traditional scheme, it is no convergence, and sometimes error even becomes higher. And the last example, this is a verification on simulation of unsteady problem of flow simulation around the sphere. We just compared pressure coefficient distribution around the meridian. Yeah. And for this slide, this is the dependence of the lift coefficient and torque coefficient for the wing of the finite span, independence on the angle of incidence. Okay, as a result, I don't know, I'm not sure that it is necessary just to read it once again. Thank you for your attention. Thank you for your question. I will try to answer them.
Well, first of all, I have a remark that just it would have been worth during the previous presentation explaining the audience what is T scheme, because there it was announced but nothing was said what is about. And so, but finally in your presentation, I understood what it means. But it's better if something is declared, then it should be explained. So it's very good. And just the problem, this T scheme, just is solving a steady state or unsteady state problem. Which problem is under consideration?
Of course, the main interest of considering of unsteady problems, naturally. But if we just study the mathematical model arising important method, we can see that at every time step in unsteady simulation, we should solve nearly the same equation, and the difference will be only connected with the right-hand side of this equation, which expresses the influence of vortex wave. Of course, vortex wave is unsteady, but at each time step, we just simulate the generation of additional vorticity on the whole surface. It doesn't matter in two-dimensional problems or three-dimensional problems, idea is nearly the same. So in order to just to verify numerical schemes and so on, sometimes it's suitable to consider steady state problems because idea is absolutely the same. The accuracy doesn't depend on the fact if we consider unsteady case or steady state. So the mathematical model is more or less the same.
Yes, so that's why that was my guess, that the accuracy is the same. So even in case you are simulating steady state problem, you have accumulation of error for successive time steps. And the question is, did you try to evaluate this accumulation of errors with the number of time steps for your scheme? Because I did these estimates for many different schemes, but I see your scheme for the first time, and of course, the estimates of error accumulations were not done. And so, have you done it, and how it just looks like, how it grows with time, so something like that? Can you comment?
Yeah, I'm not sure that I can exactly answer your question, but
definitely not.
Idea is nearly the following. For example, if we consider both report I have mentioned of report from Sandy Laboratory and also some results obtained by Professor Dimitrova, they just write down the integral equation with respect to vorticity flux. So this is some speed vorticity generation, on the surface. If we try to solve this equation exactly, I mean with respect to vorticity flux, the accumulation of error will be dramatic. But in our in the framework of our approach, we take some simplifications, some assumptions. The main assumption is the following: we use some kind of implicit scheme. So we just perform time step. We consider vorticity generated during this time step to be distributed in thin vortex sheet, and we just solve the problem implicitly and determining its characteristics, its intensity. And so our scheme, in some sense, is self-correcting scheme or something like it. And this is very, very important feature. Thank you for your question.
Okay, thank you.
Okay.
Thank you.
Okay, thank you.
Thank you.
And next is hello, dear colleagues. I'm glad to present my work at this conference, APM 2021. For my report, my report is devoted to a non-isothermal Newtonian fluid flow through an axisymmetric and contraction. The main aspect which is considered in this work is thermal boundary conditions assigned on the solid mode. But first, let me explain why it is important to study these kind of problems. Pipelines with phase-like contractions are frequently used in various industrial equipment, which is used to transport liquid media. For example, when processing polymeric compounds by casting method, So in general, all the flows are accompanied by viscous dissipation, and that's why we should consider these flows under non-isothermal conditions. And what else? If we consider it under non-isothermal conditions, we can study in details the working mode of different industrial equipment to provide reliable and safe working modes. Here is the list of the main purposes of the work. So we aimed to simulate numerically a steady non-isothermal viscous fluid flow through a sudden pipe contraction. We also wanted to obtain and analyze distributions of velocity, temperature, and apparent viscosity depending on dimensionless parameters, and to study the impact of thermal wall boundary conditions on the flow structure and local energy losses. So we consider a laminar, steady, non-isothermal flow of viscous incompressible fluid in an axisymmetric sudden pipe contraction. Here you can see mathematical formulation of the problem, which is presented in dimensionless form using the string function, vorticity, and temperature variables. Formula 4 determines the temperature-dependent apparent viscosity of the fluid. And you also can see the dimensionless parameters of the problem. At the inlet boundary, the velocity and the temperature profiles are calculated corresponding to the steady state flow of Newtonian fluid under non-isothermal conditions at a constant flow rate to define the inlet boundaries condition. In the outlet boundary, the derivatives of the required functions, I mean stream function, vorticity, and temperature, are assigned. The derivatives with respect to zero are set to zero. With respect to z, are set to zero. Along the symmetry axis, the symmetry conditions are assigned, and what is for rigid wall? In this case, we use constant wall temperature. And the short form of this case is CWT. I will refer it with this abbreviation. An alternative wall boundary conditions is named as mixed wall boundary conditions. It means that the part of the wall is exposed to a constant wall temperature, and the part of the wall, the part of the wall in the contraction plane vicinity is exposed to a constant wall heat flux. During the numerical simulation, the derivatives of the required functions with respect to pseudo-time were introduced in the main equations. You can see these derivatives. It is done in accordance with the full-strengthened method. Discretization of the main equations was made using the finite difference method based on the alternative direction scheme. And the resulting system of equations, which are algebraic, is solved using tridiagonal matrix algorithm. A set of calculations were implemented in order to verify the developed numerical algorithm. Verification is performed for both considered cases, as you can see. So the maximum axial velocity and the maximum temperature attained in the contraction plane and in the exit sections are presented for the MWBC case in table 1. And the velocity and temperature profiles along the contraction plane for the case CWT are presented in figure 2. All these results show the approximation convergence of the algorithm with mesh refinement. Further calculations are implemented with the grid step of 0.025. Let me pass on to the obtained results. So here you can see the flow patterns represented as streamlined distributions for the case CWT and MWBC in figures 3A and 3B. Both these patterns include one-dimensional flow regions in the inlet and outlet vicinities, and here we can see that the streamlines are parallel to the pipe wall here and there. But what is for contraction plane, we see that here the streamlines have curvatures, and we also know that here are two-dimensional flow regions. And what else? We see additional distortion in the case of MWBC. This is the result of the presence of radial velocity in this region. And the axial velocity distribution for both cases are presented in figure 3, EF. The next are the temperature distributions for various sets of parameters. What we can see is that considering these first four cases, we can say that increase in the Reynolds number does not significantly affect the temperature contours, but if we consider these four cases, I mean the last four cases, an increase in the Peclet number affects the temperature contours significantly. As you can notice, the region with higher temperature is shifted towards the outlet section. In this case, when you make numerical simulation, you should keep in mind that the downstream pipe, I mean the narrow part of the pipe, should be long enough to provide hydrodynamic and thermal stabilization. And here are the corresponding distributions of the apparent viscosity. And again, temperature distributions. Here we can compare how the temperature varies if we use different pipe contraction ratios, as you can see, 4:1 and 2:1. And if we vary Brinkmann number, I would emphasize your attention on the variation of Brinkmann number. If it is increased, we can notice a significant heating up in the downstream pipe. That's because of the viscous dissipation. And again, distributions of the apparent viscosity. Now let's analyze the flow structure characteristics. As it was mentioned before, in both cases, the flow included two-dimensional flow regions, and we decided to introduce dimensionless characteristics of these regions. I mean the length of the two-dimensional flow region in the upstream pipe, we denoted it by L1, and the two-dimensional flow region in the downstream pipe, which is denoted by L2. And also we introduced the length of the recirculation region in the inner part of the corner. Comparing the considered two cases, CWT and MWBC, you can notice that these flow characteristics, I mean the length of two-dimensional regions, are very similar, but comparing the structures in these two cases, we should keep in mind the presence of the radial velocity that I showed you before. And the last but not the least, let's consider local resistance coefficient. It is well known that when the real fluid flows through the pipe with sudden contraction or expansion, there are two types of energy losses. The first type is the friction energy losses, which is due to viscous dissipation. And the second type is the local energy losses, which is due to the sudden changes in the pipe geometry. So we are interested in the second type of energy losses. The local resistance coefficient is determined by the losses, by the energy losses which happen when the fluid flows into the narrow part of the pipe. So the velocity increases and we need additional energy for it. And also we need some additional energy to organize the flowing in the inner corner of the pipe. So you can see formula 5, which determines the coefficient, where alpha is the kinetic energy correction factor. So to analyze the effect of the thermal wall boundary conditions on the local resistance coefficient, we considered its values depending on the main parameters of the problem. And you can see these values in table 2. What you can notice is that MWBC case provides more efficient conditions of the flow because the values of C log are less in this case. But when we increase the parameters, this difference between these two cases becomes less. And the last thing to show is various combinations of the wall parts where the constant heat flux is specified. And what we can see is that the least value is attained when L3 is equal to 2 and L4 is equal to 3 in this case. In summarizing what I have reported today, we have performed a numerical simulation of non-isothermal viscous fluid flow through a sudden pipe contraction. We have obtained distributions of the flow characteristics and analyzed them depending on dimensionless criteria. We didn't find any qualitative or significant quantitative differences in the flow structures when compared to considered cases, except for the case when we found additional radial distributions, radial velocity distributions. And the local resistance coefficient was found to be less in MWBC case, and we find it more efficient. Thank you for your attention. Thank you. Do you have questions?
In your system of equations, you had such a term, S over Reynolds number. I missed, what is S? And how did it appear there?
S is a capital
Yes.
S. You mean?
Yes, capital S. What is it?
Capital S denotes the source term. So there are several parts of the equation, but we united it in one.
And
term.
what is this source term?
This term unites all the parts.
I see, this is, wow. Okay, I missed it.
Just to make
Excuse
it
me.
shorter.
Yes, to make sure. Okay, then that's clear, absolutely. And then also there is such an equation. You are solving, as I can see, always steady state problem.
That's right. But
And so,
according to the
what did,
but we added some derivatives according to the post-Henry method, and then
well, it's
then it
just
becomes zero.
as a method
Yeah.
of solution. But since you assume that there exists a stable, steady state solution. And what is the basics for these assumptions? Because there are very many solutions, just problems which do not have stable, steady state solutions. Just streaming of the sphere with the vortex. Just flow in a channel of the type you have with a heat release. Well, here I think there is a person who simulated this problem and found that actually, despite of all symmetry of boundary conditions, the solution is unstable. There exists such an oscillations in compressible gas. I don't know, maybe it's fluid. So what made you think that the steady state solution is stable? Because you are searching it as if it is stable, but what are the hints that support this point of view?
I understand the question. So, as I mentioned, we solved a one-dimensional problem to specify the boundary conditions in the inlet section. So we can solve the problem partly. I mean, the wider part of the pipe and the shorter part. So we take it long enough to do so that the contraction plane doesn't affect the flow in the inlet vicinity and outlet vicinity. That's my answer.
Okay, doesn't affect, that sounds strange because you have subsonic flow. So, or supersonic.
No, it's laminar.
I mean subsonic. So it's below, the velocity of the
Yes.
flow is below the speed of sound.
Yes.
And in this case, for the steady state problem, both the initial, the entry and the outlet, they feel the contraction. Because steady state problem is the problem for time tending to infinity. And since disturbances propagate in both directions, they should just affect it.
They
It's
appear,
the basic theory. So you showed that they are small. But nevertheless, inside there could be oscillations which are small. Okay, thank you. Excuse me, took already a long time. Thank you very much. I'm quite satisfied with your answer.
Thank you. Okay, so yes,
One question to you. When you were considering your boundary problem condition, was it for a flow restriction when the fluid traveling through the pipe was plowing at a horizontal direction or through a vertical?
through horizontal?
Through a horizontal.
Yes.
So we are considering a vertical, this case would not apply.
You know, in this case, we should account for another forces.
Okay. That's all I had.
We will have additional terms in equations, and I think it will be applicable as well.
Okay. Thank you.
Okay, thank you. Yes, and the next talk is from Yulia.
Добрый день, меня зовут Chairperson Юлия, я студент МГУ имени Баумана. Сегодня я хочу вам представить доклад «Гибридная модификация, основанная на идеях метода Барнса-Карта и метода мультиплон для двумерной задачи обтекания профиля». Вихревые методы вычислительной гидродинамики являются эффективным инструментом решения задач обтекания профилей несжимаемой жидкостью, а также для решения задачи сопряженной постановки. Математические модели вихревых методов применимы также для вязких течений. И также стоит отметить, что вихревые методы являются эффективным способом для решения задач внешнего течения. На экране представлены несколько групп ученых, а также представлены их работы. На экране представлены несколько типовых задач, которые можно решать вихревыми методами. Правый столбик — это недвижимый профиль, а левый столбик — движимый. Повторюсь, что в вихревых методах частицами являются носители завихренности. Таким образом, первичной переменной, которую мы ищем, является поле завихренности. Таким образом, уравнение на вес токса можно рассматривать как уравнение переноса завихренности с некоторой скоростью. В области течения завихренность можно представить как систему n-вихрей с помощью некоторой формулы. Эти вихри заданы своей циркуляцией гамма. Таким образом, чтобы вычислить конвективные скорости, можно использовать обобщенный закон Биоса-Варана. Скорость в нашем случае обусловлена скоростью набегающего потока, скоростью, обусловленной завихренностью, а также скоростью, обусловленной влиянием профиля, на котором расположен вихревой слой. Рассмотрим задачу восстановления скоростей, а конкретно второе слагаемое, которое представлено на экране. Влияние происходит каждый вихрь на каждый, собственно, поэтому нам необходимо n квадрат операций для вычисления этого влияния. Такая задача похожа на задачу n тел. Для решения задачи n тел существует два иерархических метода: метод Барнса-Хатта и метод мультиполей. Однако эти методы были разработаны для гравитационной задачи, в которой в качестве частиц мы используем тела, заданные положительной массой. В гидродинамической задаче в качестве частиц мы рассматриваем носители завихренности с циркуляцией, которая может быть разных знаков. Известна модификация метода Барнса-Хатта, она принадлежит профессору Дынниковой. Хочу обратить ваше внимание на верхнюю картинку. В классическом методе Барнса-Хатта главной идеей является группировка всех вихрей в один, а также нахождение влияния от всей группы как от влияния одной частицы, расположенной в центре массы. В гидродинамической задаче центр завихренности может находиться вне данной области или даже на бесконечности. Соответственно, поэтому предложено полимерной рассматривать отдельно положительные и отрицательные вихри. Но при этом нам необходимо 2 раза проходить алгоритм, что приводит к тому, что нельзя модифицировать данную работу к 3D-случаю. Также известен мультипольный метод. Он основан на локальных и мультипольных разложениях, с помощью которых можно объединить также группы частиц в один. Хочется отметить, что метод мультиполей является особенно эффективным при вычислении достаточно большой точности, которая не нужна в нашем случае при решении вихревыми методами. Также хочу сказать, что в методе Барнса-Хатта, в свою очередь, есть параметр, который позволяет контролировать необходимую точность. Таким образом, целью нашей работы стоит создание и реализация метода, который совмещает в себе положительные качества каждого из методов. Стоит отметить, что обход дерева в методе Барнса-Хатта позволяет вычислять некоторые другие операции в вихревых методах. Они представлены на слайде, а также представлены их доли в алгоритмическом алгоритме. Целью всей работы является разработка эффективного метода, основанного на идеях метода Барнса-Хатта и метода мультиполя с измененной вычислительной сложностью, применимая для многих операций вихревых методов. Перейдем к идее метода Барнса-Хатта, поскольку весь алгоритм основан на алгоритме метода Барнса-Хатта, однако каждый из этапов имеет свои особенности. Например, первый – это построение дерева, производящееся делением области пополам. Строим дерево до тех пор, пока не достигнуто максимальное значение, изначально заданное, это глубина дерева. Вторым этапом мы вычисляем параметры ячеек, о них мы поговорим чуть позже. Третье – это деление ячеек на дальние и ближние с помощью параметра θ, параметр близости. Четвертый – это вычисление скоростей. В ближней зоне мы вычисляем по точной формуле вируса ВАР, в дальней зоне с помощью приближенного расчета. Перейдем к идеям, которые принадлежат мультипольному методу. Во-первых, разложение функцию влияния кластера можно разложить так, как показано на экране. Это позволяет нам записать скорость, как записано во второй формуле. При этом переменные, обозначенные красным цветом, принадлежат и зависят только от влияющего кластера. Таким образом, они позволяют вычислить мультипольные моменты. В силу симметрии тензоров мультипольных моментов мы можем их определить всего с помощью двух чисел, а также стоит отметить, что вычислять их нужно всего один раз для всего влияющего кластера. Во-вторых, можно уменьшить вычислительную сложность с помощью того, чтобы объединять точки наблюдения в контрольный кластер и находить влияние на него, а потом с помощью локального разложения повышать точность. Такой подход позволяет нам использовать несколько схем для различной точности. В таблице указан порядок разложения Тейлора для каждого мультипольного члена. На верхнем графике мы видим, что 4 схемы нашего алгоритма позволяют определить линейную вычислительную сложность, в то время как прямой алгоритм имеет сложность ОН квадрат. На нижнем графике указана относительная ошибка, зависящая от параметра θ, параметр близости. Следующей задачей, которая является максимально важной, является решение ограниченно-интегрального уравнения. Заметим, что ядро интегрального уравнения почти не отличается от функции влияния кластера, однако его нужно умножить на орд касательный. Можно решение представить несколькими способами. Для первого, самого простого способа, можно прямым методом использовать модификацию быстрого метода, так как при традиционном решении СЛАУ матрично-векторное умножение мы можем выполнять с помощью быстрого метода. В данной модификации мы завихренность воспринимаем как точки. В более сложных схемах 2 и 3 завихренность нужно модифицировать, для этого мы используем мультипольное разложение. Для последней схемы, которая была на предыдущем слайде, представлена матричная форма записи левой части уравнения, системы уравнений. При умножении блоков, которые указаны красными прямоугольниками, мы будем использовать быстрый алгоритм. На нижнем правом графике указаны результаты, полученные гибридной схемой, где в ближней зоне мы учитываем результат точно, в дальней мы используем уже известную модификацию. И я хочу отметить, что для того, чтобы получить точность, соизмеримую с точностью, получаемую прямым методом, то есть пунктирные линии, нам необходимо брать достаточно маленькое тета, что, например, в данном случае приводит к тому, что 90% мы вычисляем точным способом. И, соответственно, мы не используем быстрый метод максимально эффективно. В новой модификации параметр тета достаточно большой, соответственно, считает гораздо быстрее. Для того, чтобы еще ускорить наше матрично-векторное умножение, мы используем предобуславливатель. Портрет матрицы предобуславливателя вы видите на экране, и это приводит к тому, что мы можем использовать модифицированный метод прогонки. Как вы можете увидеть в таблице, количество матрично-векторного умножения в методе GMLS уменьшается примерно в 2 раза, а в первом методе изначально он не сходится, затем он начинает сходиться. На экране представлено время, а также ускорение при использовании прямого алгоритма, а также быстрого метода. Хочу отметить, что первые 2 строчки основные операции данного метода мы получаем ускорение более чем 70 раз, в то время как остальные операции начинают меньше, потому что используют в основном обход дерева. Максимальное ускорение составляет 32 раза, что получается значительный результат. В заключение хочу сказать, что мы получили новую модификацию, которая имеет безлинейную сложность. Также хочу сказать, что эта модификация позволяет выполнять основные операции вихревых методов, а также особое значение имеет то, что эту схему можно использовать для решения интегрального уровня. Спасибо за внимание. Ваши вопросы.
Спасибо. Так, если у нас вопросы или пора двигаться дальше, то мы задерживаемся немного. Хорошо, если вопросов нет, то давайте тогда к следующему. Фаткулина Назгуль, пожалуйста. Yes, Фаткулина Назгуль, sorry.
Good afternoon. My name is Nazgul Fatkulina. I represent the Center for Micro and Nanoscale Dynamics of Disparate Systems, Bashkir State University, Ufa. I would like to present my research devoted to the 3-dimensional simulation of the deformable droplets in microchannels with hydrodynamic traps. 3-dimensional simulation of the viscous fluid flows in microchannels with hydrodynamic traps is of great importance for microfluidics. The microfluidic devices are widely used in various fields of science and industry. The efficiency of the devices depends on their optimal geometrical parameters. Thus, the primary purpose of my work is to study the dynamics of deformable droplets under flow in a microchannel with hydrodynamic traps and choose the optimal trap configurations for droplets fixation using the accelerated boundary element method. We consider the deformable particles dynamic constant volumetric flow rate. The droplets move in Carrier liquids in rectangular microchannel around the non-deformable hydrodynamic traps, as you can see on this picture. It is assumed that all processes take place under isothermal condition. The flow occurs quite slowly at small Reynolds numbers. Thus, dynamics of the system is described by the Stokes equations number 1. At the interface between the droplet and Carrier liquid, velocities are equal, and the difference of normal stress vectors is set. At the inlet of the channel, a constant volumetric flow rate is set. Also, we set the non-slip condition at the trap surface. The motion of deformable droplets is characterized by kinematic condition number 4. We use a numerical approach based on the boundary element method. BEAM is often used when solving three-dimensional problems or problems in domains with complex geometry. The main idea of the boundary element method is as follows. The original partial differential equations describing the behavior of the unknown function inside and on the boundary of the domain are transformed into integral equations that connect only the boundary values. Consequently, it is not necessary to discretize the entire three-dimensional region. Only the surface of the elements is covered by the triangular grid. Application of the boundary element method allowed to reduce the dimensionality of the problem by 1 because all calculations are related only to the boundary of the considered objects. The boundary integral equations of the problem on the flow of a viscous fluid occupying a certain volume bounded by the surface S are written as follows on this slide. Using quadrature formulas of the boundary integrals using the method of collocation in the vertices of the grid, we obtain a system of linear algebraic equations with a dense asymmetric matrix. Here we can see the boundary integral formulation of the problem of the flow of a viscous incompressible fluid around fixed, non-deformable elements of the traps. Below is the boundary integral formulation of the problem of the dynamics of deformable droplets of one liquid in the volume of another viscous liquid around the non-deformable elements of the hydrodynamic traps. As the size of the problem increases, the use of non-accelerated standard boundary element method becomes more difficult. There is a problem of lack of memory of the computer system. To solve this problem, algorithmic and hardware acceleration of the standard BEAM is used. The direct method of solving the SLAE is replaced by the iterative method. And also the standard matrix vector product is accelerated using the fast multiple method. It is known that the standard MVP is transformed to the calculation of sums as by the following formula. The basic idea of the fast multiple method is that the matrix kernel can be factorized. It means that it can be represented as a sum of products of functions that depend on x and y only, and it is assumed that such a series is convergent and can be truncated to the first p elements, as you can see on this formula. By varying this parameter p, we can change the accuracy of the results of the matrix vector product. Thus, we were able to reduce the overall computational complexity of the method used from quadratic to linear. This allows direct 3D simulation of the dynamics of dispersed systems in complex areas, the surface of which is covered by many thousands of triangular elements. C-shaped traps are often used in practice to trap and fix particles. In this work, we consider two configurations of traps. The first one consists of 4 cylindrical elements of the same size arranged in a C-shape. The second consists of 5 similar elements. The distance between the elements in each trap is very small, but not zero. This configuration minimizes the hydrodynamic resistance in the channels of the microfluidic device. Consequently, the flow rate increases and the efficiency of the device increases too. This slide shows the streamlines and velocity components of the fluid flow around the C4 and C5 hydrodynamic traps. The liquid flows around the trap both outside and in the area between the cylindrical elements. The element located in the center of the C5 trap creates an additional hydrodynamic resistance. Thus, in the center of C5 trap, the flow rate is very small. In the center of C4 trap, there is an area with a higher velocity. In this case, the probability of a drop hitting in this region increases. On this slide, we can see the streamlines and velocity components of fluid flow around a triangular array of C4 and C5 traps. The total number of traps was 15. The computational domain was covered by a triangular grid consisting of more than 300,000 triangular elements. The distance between trap rows was 2L, where L is the width of the trap along the x-axis. Initially, in the channel there is a parabolic profile of the fluid flow. Over time, it redistributes so that the highest flow rate is observed near the walls of the microchannels, as you can see on this picture. This slide shows the chess arrangement of traps. The total number of traps was 22. The distance between the rows of traps was also 2L. The number of triangular elements was more than 400,000. The figures show the streamlines, longitudinal and transverse components of the fluid flow, around the trap array. The areas with the highest velocity are observed between the traps, as you can see on this figure. In all cases, inlet pressure is constant. The resultant Reynolds number varies between 4/10 and 7/10. We considered the dynamics of droplets of different sizes. The distance from the center of the droplet to the trap was 5d. At the initial moment of time, you can see on this video, the particles were located on the central axis of the trap and had a spherical shape. As time passes, the droplets move in the flow, deforms, and when it reaches the trap, it is fixed in it. On this slide, figure 1 shows the dependence of the velocity of the mass center of the particles on time. The larger droplets are trapped faster compared to the smaller ones. Figure 2 shows that the fixation of the droplet by the C4 trap is faster than by the C5 trap. We consider dynamics of the several droplets in microchannels with trap arrays with different arrangement. These videos demonstrate the motion of droplets in a channel with a triangular array of traps. Droplets pass by triangle array of C5 traps due to the flow redistribution and hydrodynamic resistance increasing. On these videos, you can see the motion of deformable particles in a channel with a chess array of traps. This traps arrangement is more effective than triangular. It is more promising for further study. Here are the main results of the work. Thank you for your attention. You are welcome with your questions.
Thank you. Yes, please, if someone has questions. Maybe I missed, but how do you verify your results?
Could you repeat your question, please? I don't hear you.
Oh, okay, yes. Sorry, I forgot. Yes, I forgot that we need to talk with camera. Maybe I missed, but how do you verify your results and your algorithm? And also, which computational software do you use, or it's your own developed code?
Thank you for your question. We used MATLAB, where we developed accelerated boundary element method. We write this method by another publications of the authors of my scientific advisor works. So this method is very suitable for this problem, and it is good for this problem.
So no experiments.
We don't provide an experiment, but we are going to carry out the experiment in our laboratory. I think maybe this year.
Okay.
So then we can we will able to demonstrate the analysis of computational results and experimental results too.
Okay, I see. Thank you. Thank you for.
Thank you.
Any questions? No? Okay. So the next talk is from Higai. Yes, right? Higai is here.
Я бы хотел попросить доложиться на русском языке, потому что не успел подготовить доклад на английском.
Ну, это нежелательно, если мы не успели, то что поделать.
Здравствуйте, меня зовут Хигай. Я представляю работу численное моделирование заполнения емкости вязкой жидкостью под давлением ОФ-методом. Одним из основных способов переработки полимерных композиций является литье под давлением. В работе 1.2 показано, что на механические свойства и качество конечного изделия сильное влияние оказывает процесс, стадия заполнения соответствующей пресс-формы. Такие процессы могут сопровождаться появлением воздушных включений или линий спая, что приводит к появлению внутренних дефектов и потере монолитности конечного продукта. В работе 3 также исследовался процесс формования изделий методом свободного литья. Показано, что анализ процесса заполнения необходим с целью прогнозирования качества готового изделия. Математическая постановка задачи. Рассматривается течение ньютоновской жидкости со свободной поверхностью, реализуемое на начальной стадии заполнения емкости с центральным телом в поле действия силы тяжести. На рисунке изображена область решения, которая представляет собой канал с внезапным расширением, в широкой части которого вдоль оси симметрии на определенном расстоянии расположено твердое тело. Система уравнений, описывающих данное течение, включает уравнение на вес Стокса 1 и неразрывности 2, записанные в безразмерном виде. Замыкается система граничными условиями. На входной границе гамма-1 задается параболический профиль, соответствующий установившемуся течению вязкой жидкости в плоском бесконечном канале. На свободной границе используется условие непрерывности напряжения, на твердых стенках выполняется условие прилипания. Постановка задачи включает 2 параметра безразмерных, это число Рейнольдса, и параметр W, характеризующий соотношение гравитационных и вязких сил в потоке. Сформулированная задача решается численно, конечно, разностным методом. Основные уравнения решаются методом контрольного объема с применением корректирующей процедуры Simple. Эволюция свободной поверхности отслеживается методом WOV. Для верификации программы расчета проведена проверка аппроксимационной сходимости. На последовательности сеток вычислялся закон сохранения массы по формуле на слайде, а также вычислялась ширина растекания жидкости по дну, которая на рисунке обозначена буквой S. Результаты вычислений показаны в таблице. Видно, что аппроксимационная сходимость наблюдается. Все дальнейшие расчеты проводились на сетке с шагом 1/40. Для геометрических размеров области показаны, как показано на рисунке. Результаты расчетов показали, что заполнение может происходить в одном из 3 режимов. Первый режим заполнения, при котором свободная поверхность полностью перекрывает зазор между твердым телом и плоскостью скачка сечения. И жидкость растекается по дну емкости. Такой режим реализуется при доминировании гравитационных сил над вязкими и является благоприятным режимом технологии переработки полимерных композиций. Второй режим заполнения, когда поток жидкости ударяется в центральное тело и падает на дно пресс-формы. Наблюдается, когда вязкие силы уступают инерционным, но доминируют над гравитационными силами. Третий режим, когда жидкость ударяется в центральное тело, но не обрушивается на дно, а образуются боковые струи. Этот режим возникает при доминировании инерционных эффектов над вязкими и гравитационными. Последние два режима являются неблагоприятными для технологических процессов, так как могут включать образование воздушных полостей. На рисунке приведена диаграмма режимов в координатах число Рейнольдса и параметр W. При малых значениях параметра заполнение происходит в режиме образования боковых струй. Увеличение параметра W приводит к режиму обрушения струй на дно, и дальнейшее увеличение приводит к режиму растекания жидкости по дну емкости. Волнообразная линия разделения режимов, возможно, связана с влиянием инерционных эффектов в области малых значений параметра W. И в заключение проведено исследование формирования потока жидкости во входном узле при заполнении емкости. Вычисления показали, что заполнение может происходить в одном из трех перечисленных режимов. Нет, все, спасибо.
What question? What language we have to use and answer questions?
Вы понимаете на английском? Можете отвечать на английском?
Какой язык я хочу использовать?
Нет, в смысле, можно вопрос на английском задавать?
Можно.
Okay, then we prefer English.
Yes. What criteria could be used for the pause formation during the flow? Критерии образования пор. Какой могут быть при использовании критерий? Чтобы оценить
в зависимости от параметров.
Нет, для формирования пор нужно все равно формулировать специальные критерии. Течение может быть какое угодно, и растекаться может по-разному. Но будут формироваться там поры или нет. Для этого нужны критерии формировать.
Нет, не будет сформулировано.
Нет.
А может еще один вопрос. Значит, я сталкивался с задачами заполнения формы расплавами. Там одна из проблем была, как потом вот это вот тело, когда остынет, как оно там деформируется, как-то ваш план рассмотрения таких процессов входит, не входит. Я понимаю, сейчас ориентирован. Спасибо.
То есть вопрос усадки не рассматривается.
Решите вопрос. Ну, вопрос такой, технологически вычислительный. А вы какой-то пакет использовали для расчета эффектов? Потому что я поняла,
Нет, это моя собственная программа расчета.
То есть вы не захотели это встроить в какую-то, так сказать, готовую, ну там условно скажем, молотилку типа OpenFOAM, значит, которая это реализована?
Да.
А почему?
Ну, собственно, программа расчета позволяет избежать сглаживания используемых различных пакетов.
Хорошо, тогда второй вопрос. Вот вы указали, что вы используете алгоритм Simple. В то же время вы говорите, что вы решаете нестационарную задачу. Но канонический Simple вообще-то позволяет только стационарные задачи решать.
В Simple используется метод установления, в котором присутствует нестационарное страдание, но позволяет.
Подождите, но это квази-время. Она не дает вам решение нестационарных задач, она неправильно дает решение нестационарных задач. Может, это легко убедиться. Вот стационарное будет правильно, если оно видит. Но вы-то не стационарный режим считаете?
Да.
А как вы Simple используете?
Simple позволяет.
Нет. Нет. Ну ладно, это, наверное, вопрос обсуждения.
Еще вопросы? Или следующий доклад? Хорошо, спасибо. So, next the topic is I'll do Hakima follow.
I want to talk about flutter of rectangle plates at non-zero your angle. In our work, the phenomenon of panel flutter is considered. Panel flutter is phenomenon of self-exciting vibration of skin panels of flight vehicles at high speeds. There are two types of panel flutters. Coupled mode flutter is due to the interaction of the escalation eigenmodes, and single mode flutter that occurring at low supersonic flow and without coalescence of eigenmodes. So, and different papers, the case of zero, your angle is considered, but in these papers is using some simplest aerodynamic theories, and other papers, in some other papers, the case of non-zero, your angle is considered and is more complicated aerodynamic theories is using. We use the theories of potential flow and consider panel flutter at non-zero your angle. So problem formulation is the following: the stability of infinite series of rectangle plates at non-zero your angle is investigated. One side of plate is exposed to the homogeneous supersonic flow of inviscid perfect gas. Other side experience constant pressure, so the undisturbed state of the plate is flat. Plates are simply supported along all edges, and supersonic link edge is studied. So let's introduce the X at Z system. So the gas flows along the x-axis, at axis across the flow, and z-axis normal to the plate surface. In this system, the system of equation is following. The first is a plate motion equation. The second, simply supported boundary condition. The third, the flow equation. The fourth, it's free slip condition, and fifth is expression for plate perturbation on the plate. So this is a definition of non-dimensional parameters. We consider small perturbation in this form, and so we obtain the system of the equation in such form. The solution of this equation is no and has this form, where S is a triangle that is interaction of match cone and plate surface. So we use this expression for flow potential to obtain the expression for pressure perturbation that has this form, And Mohan equation after substitution with expression for pressure perturbation with boundary condition is eigenvalue problem, and the sign of imaginary pub of eigenvalue is a flatter criterion. So the method of solution is the following. Eigenvalue problem is solved numerically with using Bubnov-Galerkin procedure. The plate deflection expressed as superposition of more shapes of plates in vacuum. And the equation for determining the complex eigenvalue has this form where K matrix is a matrix which introduce definition of material plate properties. E is identity matrix and P is aerodynamic matrix. So the result of our investigation is the following. First of all, we compute boundary of panel flutter at 0 for angle. These figures show the compression with result obtained by Yekaterina. So in these figures, Mach number plotted and vertical axis and non-dimensional length of the plate plotted at horizontal axis. Solid line denotes the result obtained by Yekaterina, and the dotted lines denotes the result of this work. So the compression shows that results are a good agreement for mode and for mode 2, for mode 1 and for mode 2. So then we compute the results at non-zero your angle. At small angle, like your angle of 5 degrees, the results goes to results at 0 angle. These figures shows results at different non-dimensional width of the plate, Ly, and in these figures, Mach number plotted in vertical axis and the non-dimensional length of the plate plotted and horizontal axis. Solid lines denotes the plate panel flutter boundaries, and region shaded with gray is a region of instability. In a large non-dimensional width and after some value of LX, there is a region of flutter in first mode where both single mode flutter and coupled mode flutter appears. With decreasing Ly, the narrowing of region of instability appears. And after certain value of Ly, region of flutter divided into a single mode flutter and a coupled mode flutter. And then single mode flutter contracts to a point and disappear, and region of coupled mode flutter shifted to region of large Lx. With increasing your angle, results becomes more difficult. In large Ly, results is close to small. There is region of flutter for first mode but with decreasing LY, on one hand, there is a narrowing of region of flutter, but on the other hand, there is additional region of flutter. In single mode flutter, one mode dominate, and at single mode flutter region A, two modes dominate, and this flutter caused by interaction two modes. But additional regions of flutter caused by interaction of several modes. And then results is close to results for your angle of 10 degrees. There is region of single mode fault, is region B, D, and G, M, and the region of single mode, coupled mode flutter caused by interaction of two modes, A, C, F, K, and L, and O, and additional regions of flutter that's caused by interaction of three or more modes, E, H, K, and N. This is example of oscillation mode of at flow of plate at region of single mode flutter. So oscillation mode is close to oscillation mode of plate at vacuum. This results of oscillation mode of plate at region of coupled mode flutter that caused by interaction two modes. And at least there is region of flutter that's caused by interaction of several modes. And we can see it transferring waves across the flow. And now at large value of your angle, results it's more difficult. There is a strong irregularity of flutter boundaries, and with decreasing of Ly, regions of single mode flutter and coupled mode flutter that caused by interaction of several modes appears. And for second mode, at a small value of your angle, results close to results at zero your angle. At large Ly, there is region of single mode flutter for second mode, and with decreasing of Ly, region decreasing contrasts to a point and disappeared. With increasing of value of angle, the region of single mode flutter appears too, but additional regions B, D, and for your angle of 20, region B, D, F, and G, this region where flutter caused by interaction of several modes. And with further increasing of your angle, the number of such regions becomes more. So conclusions are following. We computed single mode flutters and coupled mode flutter boundaries at non-zero your angle, and comparing with zero angle new regions of panel flutter appears that caused by the interaction of three or several modes. And the results of this work can be used to create methods for suppressing the flutter that caused when a big flow around the skin panels. Thank you.
Thank you.